This video is for section 11.1, a new type of test called a chi-squared test. It's also denoted by the Greek symbol chi. And I think after doing a month or so of tests that were only about proportions and only about means, these types of tests will be a nice change of pace for you. So let's take a look at the first example. And this one's in page 2 or 3 of your notes, so you might have to find it there. But it talks about zodiac signs. And do zodiac signs determine how successful you will be? Fortune magazine looked at zodiac signs of 256 heads of 400 different companies, but we only looked at 256 heads. And we looked at our zodiac signs. We have kind of a nice assortment down here of the 12 signs of the zodiac. And certainly it looks like that the plurality, were born under Aquarius, which is the same as me. And we see that the least number was with Libra and with Gemini that have 18. And our question here is, are these zodiac signs, and therefore the time of year that the CEOs were born, equally distributed, uniformly distributed, or are there times of year where it's more likely that a CEO was born? And so the idea here is there were 256 different CEOs represented here. How many should we expect to see in each group if these were equally distributed? Well, what you could do is you could take 256 and simply divide it by 12, and you would see on average how many we should expect to see in each group. And the idea of what we have, for example, under Aquarius, and what we would expect to get is what we're going to look at here. It's what we're going to measure, and it's what we're going to make a statistic of. So we'll come back to this problem again, but first some background about chi-squared tests and how they operate. First of all, chi-squared tests. They are used to test the counts of categorical data. That's a big word here. We have to have counts. It can't be weights. It can't be anything other than counts. And we'll look at 3 types of chi-squared tests. Goodness of fit, which is when we deal with one sample data. Independence, when we want to know if 2 groups are independent of each other. And also a new word here, homogeneity. And homogeneity really is a synonym for the idea of sameness. Do 2 populations have similar characteristics? Okay, so some new ideas here. And today we're going to do this first type, a goodness of fit test. Okay, so how this works, a chi-squared test has a couple attributes that we need to look at. And we'll move this up here so we can take a look at some stuff here. But essentially what a chi-squared test does is that we compare what we observe against what we would expect to have happen. And we come up with a statistic based on that. Now, when we come up with that statistic, we will use this type of curve right here, the chi-squared curve, to assess how plausible our sample data is. And it looks a little bit different than the curves we've had before. Some characteristics of the chi-squared distribution will have different degrees of freedom in these problems. You can see already perhaps that these curves are skewed to the right. They generally have this shape to them. And as the degrees of freedom increase, the curve shifts towards the right and becomes more like a normal curve. I don't want you to confuse it with the normal curve, but you start to see here with 10 degrees of freedom, it's starting to take on more normal qualities. And we'll also be dealing only with positive values in these tests. And you'll see that as we go throughout our computations here. When we do these tests, the assumptions that we need to have happen, a couple things that are the same, a couple things a little bit different. First of all, we do need an SRS. That's old stuff. We need to have a random sample from the population of interest. We need to have counts from each category, and each category has to happen at least once. We expect each category to happen at least once. What we don't want is any categories where things are really implausible, because they'll throw off our data here. And also sample size. The main condition here is that we should expect at least 5 in each category. If you think back to our data about the CEOs, we would expect about 20 or so in each category. So we'll be safe to do that test. And we'll make lists of the expected counts. Okay, when we have all this and we're all set to go, the statistic we'll compute is this one, chi-squared. And it looks much different than any other statistic we computed before, but there are some similarities here to things you've seen before. Notice the structure here. We're going to take what we observed and what we expected, and we'll subtract them. And if you think back, this idea of observed minus expected, you saw many, many chapters ago when we were talking about something called residuals in scatter plots. So it's that same idea of what we observe minus what we expect. Now, when we compute those, we're going to take those individually, we'll square them, and we'll divide by the expected count, and we will take the sum of all of those. So there'll be some grunt work here that we'll work through together. Okay? And also some qualities of the goodness of fit test. Make sure we're using one sample univariate data. We want to see how well the observed counts fit what we would expect to get. And we will also use chi-squared CDF, which is the same menu as norm CDF on the calculator to help us find p-values. So that's a lot of setup here. I think the best way to proceed is just to go back to our problem here about our CEOs, okay? And let's go through and talk about it and look at a full test, okay? So if CEOs' birthdays are equally distributed, how many would you expect in each sign if there were no difference between them? And already we see that it should be 256 divided by 12. And you can compute that on your own, but let's right now just go through the whole test. So I have it all set up ready to go here, okay? And you can follow along, and I have the formula ready to go. But first of all, we have some assumptions to make. Let's make sure all of our assumptions are met. We have a random sample of the CEOs, and all the expected counts are greater than 5, and that is, I expect that there'll be 21 1/3 CEOs to be born in each sign. That's that 256 divided by 12. Okay. What's next now is a null and alternate hypothesis. Now here's something that's going to be very different when we talk about chi-square tests. Notice that the null and alternate hypothesis are not symbol-based. They are word-based here, and this is going to be okay for chi-square tests. The null hypothesis right here is that the number of CEOs born under each sign is the same, that we would get the same number in each month or in each sign. The alternate then is that something is amiss, that the number of CEOs born under each sign is different in at least one category. All we need to prove is that at least one category is different, and therefore that will make it so that they're not all the same. All right, now the grunt work here will be computing this statistic, the chi-squared statistic. So I'm going to reveal it here, and I'll walk you through it. So the idea is we have to do this for all 12 months. We have to compute this piece for all 12 months, and then we will add them all together. And that's what's at work here. You take our first zodiac sign. There are 23 observed. There's supposed to be 21 1/3. You subtract those and square it, and you divide by 21 1/3. And this one's kind of nasty because we got those decimals floating around. And you're going to do that for each of the 12 months. The next month I have 20 CEOs born. We're supposed to have 21 1/3. I subtract them and I square it and divide by 21 1/3. And you would have to do this for all 12 months. Now doing it for 12 is a little extreme. Usually in these problems you'll only have 4 or 5 categories. But if you were to add those all together, you would get a chi-squared statistic of 5.094. And the question is, how unusual is it to get a chi-squared statistic of 5.094 if all the categories were equal? And something that's important to note here is since there's 12 months, the number of degrees of freedom is going to be 11. Now at this point, we're just going to use the p-value. We're going to find the p-value using our calculator. Okay. We will use chi-squared CDF. Our test statistic is 5.094. We want to know, let me draw a little picture here. We want to know what happens. Let me get rid of some stuff here. We want to know how likely it is that you get a chi-squared of 5.094 or worse if all birthdays are normally distributed. So I'm really finding an area from 5.094 up to infinity with 11 degrees of freedom. And I get a p-value of 0.9265. I declare an alpha of 0.05, and we know from before that that p-value is not below alpha, so therefore we will not reject the null hypothesis. Fail to reject the null. There is not sufficient evidence to suggest that the CEOs are born under any signs more than any others. So even though we saw some variation in the CEO's birth dates, and let me go back to the top here, we saw some variation here, like a 24 and an 18. It's not enough to prove that the CEOs in general are born under different signs. Okay? So the test looks slightly different here. So let's walk through one or two more examples, and we'll go a little bit faster through the next two. Okay? How about this one? This is problem 2 from your notes, and it talks about a mix of snacks, Brazil nuts, cashews, almonds, hazelnuts, and we're supposed to have certain percentages of each type. And we take a sample and we weigh them, and we see that there's a certain amount of each. So it feels like a chi-squared test. The question is, why is it not appropriate here? Well, the reason the chi-squared test is not appropriate here is that we need counts. I would need to count up the number of Brazil nuts, the number of cashews. Doing it by weight is not sufficient because Brazil nuts and almonds and cashews all might weigh different amounts. I need to count how many there are. So what might I do instead? I would need to count the number of each. Okay? Do one last example, and then be done with the video here. So we have fruit flies here, and genetic theory says that these traits will appear in these ratios. And there's 4 different traits here. There's yellow normal, there's yellow and short, there's ebony and normal, and there's ebony and short. So there's 4 different categories here. And a researcher checks 100 fruit flies, and he found that distribution here. Now what I'm going to train you to do here is to make a table. I'm going to look at the expected and what I observed. And I'm going to compare them. Well, I observed 59 of these guys, 20 yellow short, 11 ebony and normal, and 10 ebony short. So I have observed counts. Now the expected count's a little bit trickier, and I'll switch colors for this. We're supposed to have 100 altogether, and right here, the ratio tells me what I should have. So 9/16, and I get 16 by adding all those numbers together. 9/16 of them should be yellow and normal. And if I do it on my calculator, I would expect to see 56.25. Yellow and short, I should expect to see that 3/16 of the 100 are yellow and short. And you can see that comes out as, a little trouble with the smartboard, is 18.75. Ebony normal supposed to be 18.75 as well, and ebony short is 6.25. And the reason I want to show you this table here is the observed always has to be a count. These have to be whole numbers. They have to be counts. That says whole numbers. Meanwhile, the expected, it's okay if they're decimals. So observed must be whole numbers. Expected can be decimals. So now we're just going to dive right into the test. And here's all the stuff you need to know about the test. The assumptions are we have a random sample of fruit flies. All the expected counts are greater than 5. I did them in the table on the last page. The null hypothesis is that the distribution of fruit flies is the same as the theoretical model, which is the 9-3-3-9 model. And the alternate is the distribution of fruit flies is not the same as the theoretical, that at least one category is different. We only have 4 categories to compute here, so we would have to do this computation 4 times for each of the 4. We only have 3 here. We got a little lazy. But notice I have the actual count minus what was expected. I square that and divide by the expected. You do that for all 4, I get 5.671. You can now use your calculator for the p-value here. The probability that I would get a chi-squared statistic of 5.671 is 1.29. Alpha is 0.05, so therefore we'll fail to reject the null hypothesis. There is not sufficient evidence to suggest that this population of fruit flies is different than the theoretical model. So these will take a little bit more practice because the problems are quite different. But feel free to go back in the video again and review any of the problems.